In this lecture and the next, we'll be looking at alphanumeric data. This is data that represents numeric values and the characters and symbols that you have in your documents. First, we'll look at integer data. This is where the binary data represents the value of an integral number, such as these 32 bits here representing the integer value 109. We're also going to look at real number data, where the binary digits can equal a floating point number, a real number, such as 59.8568 and so on. In the next lecture, we'll look at character data, where these bits could represent the letters B, O, M, B, but also they could represent digits of a number, punctuation, or control codes, other commands. Also, we'll look at programs and object codes, how those are represented in the computer. Let's get started by looking at integer data. This is where our binary data is going to represent whole numbers. The way we read this binary data is each digit represents a power of 2. Let me explain using decimal numbers. Here we have the decimal number 4,368. The most significant digit is the 4, which is in the thousands position. It represents 4,000. And the least significant digit is 8, which represents just the number 8. 8 is actually 8 times 1, or 8 times 10 to the 0 power. When we're in the least significant position, it's our base, which is 10 to the 0 power. The next position is 6 times 10, or 6 times 10 to the first power. Then we have 3 times 100, which is 3 times 10 to the second power. And lastly, we have 4 times 1,000, which is 4 times 10 to the third power. Notice the increasing powers of 10 as we go from the least significant digit to the most significant digit. We then add these numbers up and we get 4,368, which is the number that we have represented here. Binary works in the same way. Digits are usually grouped in 8 bits, which make up a byte, or 16 bits, 2 bytes, or 32 bits in 4 bytes. So here we have 32 bits. We could group it into one large number that is 32 bits long and be able to represent a large number. We could represent it as 2 bytes, which would mean we'd be able to represent 2 fairly good-sized numbers. But in our example, we're going to break it down and have each numeric value represented by 8 bits, or 1 byte. Now let's look at this particular byte and see what it represents in decimal numbers. The most significant bit here is on the left, and the least significant bit is on the right. Binary numbers are representations of a power of 2. So each position here is a power of 2, whereas when we worked with decimal numbers, it was a power of 10. So the least significant bit is going to be 2 to the 0 power times whatever the value there is, which is 1. So we have 1 times 2 to the 0. 2 raised to the 0 power is 1. So we have 1 in that position. Next, it's 0 times 2 to the first. 1 times 2 squared, which is 4. 1 times 2 to the third, which is 8. Next is 0 times 2 to the fourth. 2 to the fourth is 16, but we're multiplying it times 0, so the result is 0. Then we have 1 times 2 to the fifth, which is 32. And 1 times 2 to the sixth, which is 64. And lastly, we have 0 times 2 to the seventh, which is 0. If we add these numbers up, we get the value 109. And that's the decimal value represented by these 8 bits. We can convert each of the other bytes to a decimal value in a very similar way. Now, depending on the number of bits we use to represent an integer number, it gives us a various range based on 2 to that power. So if we have 1 bit, 2 to the first power is 2, and we can represent 0 or 1, and that's what we have here. Each bit can either be 0 or 1. If we have 4 bits to represent our numbers, we could represent up to 16 different numbers, which is 2 to the fourth. It gives us a range from 0 to 15, and that's what we have whenever we're working with hexadecimal numbers. If we have 8 bits or 1 byte, we can represent 256 different values, which is 2 to the 8th, and our range goes from 0 to 255. With 16 bits or 2 bytes, we can represent over 65,000 different values, and so we can represent from 0 to 65,000. But that's not very big. Frequently, we need numbers that are much, much larger than that. So if we use 4 bytes to represent our integers, we have 2 to the 32nd power, because it's 32 bits, and we have a range from 0 to a little bit over 4 billion. So we still can't represent every person in the world. We need to go to 64 bits. So far, we've only represented positive numbers. Well, there's a way to represent negative numbers, and it's called 2's complement representation. What we do is we take the leftmost bit, what used to be the most significant bit, and it now becomes a sign bit. If it's 0, it means we have a positive number. If it's a 1, it means we have a negative number. Here we have 2 binary sequences where all but the sign bit is the same. So we have 7 bits that are the same in both of these, the sequence 10, 10, 101, but the sign bit is set on the right sequence. And let's look and see how these would be translated into decimal numbers using 2's complement representation. On the left, we have a positive number, so we can translate that into decimal just the same way we translated the previous number. The rightmost position is 1 times 2 to the 0 power. Next, we have 1 times 2 squared. Next, we have 1 times 2 to the 4th power, which is 16. And then we have 1 times 2 to the 6th power, which is 64. If we add these up, you get 85. Now, for the 2's complement representation, we have that sign bit set. And what that tells us is the first thing we do is we complement all the digits. So every time we have a 1 in our number, we turn it to a 0. So the first thing we'll do is create the sequence 0, 0, 1, 0, 1, 0, 1, 0 that represents each of those original bits flipped to the opposite. Then we add 1 to that sequence, and it gives us our new sequence, and we'll figure out what this represents in decimal. We have a 1, then we have a 1 in the 2 to the 1st power, which is 2. Then we have another 1 that will give us 8, and then we have a 32. We add those up, and it gives us 43. Now, because the sign bit was set, we need to remember that it's not the number 43, but it's a negative 43. So this is how we'd convert a 2's complement number. Now, what we gain by having negative numbers, we lose in the maximum value we can represent. Our range, the total number of values we can represent, is still the same. But instead of going from 0 to our maximum, we now have our range centered on 0. For example, with 1 byte, we can represent 256 values. If we only represent positive or unsigned values, we can go from 0 to 255. But if we're going to have signed values or negative values in our range, we need to move our range so that it's centered on 0, and our range will go from negative 128 to 127. The way we figure out the range is it goes from 2 to the n minus 1 power for a negative number, and then 2 to the n minus 1 power, and then we subtract 1 from that, and that gives us the maximum for our positive. So even though for each of these sequences with 1 byte, 2 byte, or 4 bytes, we still have the same total number of integers we can represent, the maximum is smaller because our range is now centered on 0 instead of being starting at 0. We can also represent real numbers, and this sequence of bits could be a floating point representation of some real number. There are 2 ways we can represent real numbers using the IEEE floating point standard 754 for data storage. One is 32-bit precision, or using 4 bytes to represent our real numbers. This gives us the range from 10 to the negative 38, which is a very small number. It's 1 followed by 37 zeros, and then a digit after that, to 10 to the 38th power. We also have 64-bit precision, which is 8 bytes, and that gives us a range from 10 to the negative 308 to 10 to the 308th power. And what we do is, by getting this incredible range, we're going to sacrifice some of our accuracy. The way floating point numbers are stored is it's approximation. Real numbers frequently are approximations because we have sequences that could repeat forever. New numbers such as pi never end, and so we can't exactly represent those in the computer. And the IEEE floating point representation allows us to get fairly accurate and still provide a fairly large range of values. Floating point numbers consist of 3 fields. So if we look at these 32 bits, they consist of 3 fields, 3 ways to interpret this long number. First is a sign bit, similar to what we had when we did 2's complement to get our negative numbers. The sign bit will tell us whether this is a positive or a negative number. And just like with our 2's complement, if it's 0, that means the number is positive. Next we have our exponent. This is 2 raised to whatever power we're going to represent. Now this exponent is not a straight conversion to an integer and then 2 raised to that power. It's an excess 127 notation. It's fairly complicated to figure this out. We're not going to go into it here because you'll probably never actually have to do that. The computers will take care of it for you when you need to look at some of this data. And then the last part is the mantissa in our exponential representation. The mantissa gives us the details of what the numbers are. And we use 24 of the 32 bits to represent the mantissa. So using the IEEE floating point representation, this would be the number 59.85681915283203. And those are some of the basic ways we represent numeric data in the computer.